14.7, Part 2. In Part 1, we were introduced to this theorem using Jacobians, and we did one example. What I'd like to do here in Part 2 is two more examples, both of which are from the book. The first example I want to look at is this one. We're integrating over a region R using these transformations. Well, when I see something like this, I go hold the phone because I was just handed the transformations. And I have a sneaky suspicion that in the future I'm going to have to find my own transformations. So, where did these transformations come from? Well, I want to show you. If you look at the integrand, you'll see that the factor y minus 2x is a serious problem because of the radical. Sometimes when I'm trying to choose my change of variables, I will choose the problem, the thing that's causing me a problem, I'll choose that as one of my variables. And in fact, that's exactly what they've just done. Now, what's left is 2x. Once I've chosen v equals y minus 2x, I might be tempted to say, well, u is just 2x. What's left over? And in fact, that would be fine, but oddly enough, that's not what they did. They didn't choose u to be 2x. If they had, then it looks like it would be a pretty simple integrand, and it is. For some reason, they chose u equals 1/2 of x. And the thing that, the reason why they chose that is it makes for some kind of a fun boundaries. But any of these three choices would have worked. And in fact, any scalar multiple of x would work. So let's go through the process that we learned in Part 1. Our first job is to find our region R. Well, we have these four vertices, and we want to just plot them, and that'll give us our region R. And this is our parallelogram. The next step is to find our new region S. Well, I said it like it was so simple, but it's not. We got to do a little work before we can find S. What we do is we write u and v in terms of x and y, and you have to do a little bit of algebra in order to do that. So you start with the transformation, and then you find u as a function of x and y, and v as a function of x and y. And then when you have a point 2, 5, now that's in the xy plane. So 2 equals x, 5 equals y, and then put that value of x and y into these two equations, u equals and v equals, and I get the point 1, 1. And now what you need to do, I've done one of them for you, what you need to do are the other three vertices. That's all you do. You don't have to do the whole thing, just the vertices. And you get that the new region is a 1-by-1 box. Now, if we had used the other choice, what was our choice? U equals twice of x. Then our u boundary there would be different. But it would have just played out differently. We would have been fine the way with any of those choices. Next, we want to find the Jacobian. And so we find all our partials and find the matrix and the determinant. And now find the new integral. And lastly, integrate. Once we have found our new boundaries, and the new transformation, the integration is pretty straightforward. That was the whole point, was to make the integrand easier to work with. And we get a value of 16/9. So these are our two solids. We were integrating over the solid on the left. That was using the parallelogram. And then we changed our region from a parallelogram to a square, a 1 by 1 square. And that gave us a new solid, but not a new volume. I'd like to now do a change of variables for triple integrals. The biggest change, of course, is going to be your Jacobian now is a 3 by 3 determinant. Use a change of variables to evaluate this integral where d is given by these planes. Now this is kind of fun because this time we're going to be creating our own transformation. So I'd also like to point out this. In the previous problem, we did a change of variables primarily to simplify the integrand. Our region ended up simpler too, but that was a byproduct. In this problem, the integrand is fairly simple. We don't need to do a change of variable because of xz. That's very simple. But we are looking to integrate over a simpler solid without making the integrand too complicated. Now, the really nice thing is D is made up of 3 sets of parallel planes. How do I know that? Well, I'm looking at the solid right now that they gave me. For me to figure that out myself without graphing it, I would have to do the following. I would have to play around with the equations given me, the 6 equations given me for the 6 planes. And if I did that, I would get these 3 sets of parallel planes. How does that help? Well, I'm just going to call u equal to y minus x. I'm going to call v z minus x and w z. So I'm not choosing my new variables based on the integrand. I'm changing my variables based on the region. And when I do that, wow, look how simpler my bounds are. U is going to go from 0 to 2, v is going to go from 0 to 3, and w is going to go from 0 to 4. And my new region is going to be a rectangular solid. All right, so we've chosen u, v, and w. What is our new transformation? Now, last time they gave us the transformation and we had to figure out it in terms of the u and v. Here, we need to find our new transformation. We're doing the whole thing ourselves. All right, well, I'm going to start with the simplest equation. I chose w equals z, and so for my transformation, that's going to be z equals w. Next, what will x be in terms of u, v, and w? So I'm doing x next. Well, the bottom 2 equations in purple or red, whatever that color is, the bottom 2, if I play around with them, I'll figure out what x is. X is equal to w minus v. Now lastly, let's do y. Well, look at your top equation and then use the fact that we already know what x is, and then y just pops out. Now that we have our transformation, let's find the Jacobian. So very nice, our Jacobian is made up of scalar values, and so when we the matrix is made up of scalar values, so that when we find the determinant, it's not too ugly. In fact, it's fairly simple, Jacobian of 1. And then we find the absolute value of the Jacobian and our new dv. And our new variables are u, v, w, so our new dv is du, dv, dw. All right, so we've got our transformation, we have our Jacobian times our dv, we have our boundaries. It's time to write our new integral. All I have to do is, instead of the x, I just put in w minus v, and instead of the z, I put in w, and then I just put in my boundaries in such a way that there's a matchup with the u and the u boundaries and so on. The last step is to integrate, and I'll leave you with this slide right here. I think that finding the integral for you will be fairly straightforward. All right, I'll see you in the next section. Have a good day.